Welcome back, everybody. So today we're going to look at the Taylor remainder theorem in a little bit more detail than in class and try to give kind of a shorthand version of what the proof would look like. And so the Taylor remainder theorem is here to figure out what the error is in approximating a function with a Taylor series. So we have this remainder term, which we call our n of x, that is going to be represented by this Taylor, this n+1th Taylor term. So the n+1 term of a Taylor series where we're centered at our particular function value c, let's say. And so there's some value z on the interval that we're concerned with. So somewhere between x and c. We can find the exact error in measuring our function by using this remainder term. Now in reality, the remainder term is going to be what we use to create an upper bound. So we'll call it the Lagrange error. And so this n+1 derivative of z is going to be really hard to find for a lot of functions. Not for every function, but for a lot of functions. And so we're going to use this essentially to say that, well, at worst, our error is going to be less than or equal to something close to what this exact value should be. So to start, though, let's actually just look at the error in measuring a power series with a function representation. So, or a function with a power series representation, I should say. So suppose we have this function 1 over 1 minus x on the interval I, where I is -1 to 1. So we've got this familiar function, which we know is going to be expressible as this infinite series. So in this case, because we have exact equality, it's actually going to become really easy to just find the error measurement here. So we'll just note that if we take a particular value, so let's suppose we want to find the error in measuring f of 0.5. Pretty easy to calculate here as 1 over 1 minus half, or 0.5, which is going to give us 2. So at 0.5, our function is equal to 2. And then for our series expression, well, we could plug in a bunch of 0.5s and use it as a calculation. But suppose that we just took, let's say, the third order approximation of that series. So we call that the Taylor series of order 3, centered at, in this case, we're going to be centered at 0. So that's going to look like 1 plus 0.5 plus 0.5 squared plus 0.5 cubed. Our coefficients are all 1, so we can just plug in 0.5. So it's order 3 because the largest degree is 3. So that's our order 3. So when we calculate this, we'll get 1.875, or 1 7/8. And so we know actually that the exact error is going to be 0.125, 2 minus 1.875, which is equal to 1/8. Okay, so this is going to be 0.125 off of the actual value, which is somewhere around like a 6% error, something like that. But the question is well, how do we know, how well is it going to be usable to use the remaining terms of our expression to somehow show that this is the case? So in other words, could I calculate this value 1/8 without actually having to do this computation? Because, if I had the 83rd order term and I've got 83 of these terms, I don't want to have to write this out every single time. So this is obviously a very simple case where we only have 4 terms total. So what we'll notice here is that f of x equaling 1 plus x squared plus x cubed, etc., that we could rewrite this as f of x minus, and then subtract over that that third order Taylor series. So 1 plus x squared plus x cubed. And if I move those terms over, what I'm left with is everything else. Right, so I still have all of those terms going on forever. And so if we take the absolute value of that, this is going to be the error. The error is the sum of the remaining terms. So where this becomes difficult is, can I actually compute the sum of the remaining terms? And in this case, the answer is yes. So we'll have x to the fourth times 1 plus x squared. So we can factor out this x to the fourth and notice that we get our infinite polynomial again here, which means that this is equal to x to the fourth times 1 over 1 minus x. All right, so we know that those are equivalent on our interval -1 to 1. So what this means for this particular series is that r sub n of x, the nth order remainder term or error term, is x to the fourth over 1 minus x, again, in absolute values, which is pretty amazing, right? Because now we've got this closed order expression for the error. And if we look at it closely, our third order Taylor is going to be computable using a order 4 term. It's not the Taylor polynomial itself, but this is going to be order 4, whereas this was order 3. So it looks like in this particular case, our error approximation is going to use an order 4 term in order to find the order 3 error approximation. And so we can test this out. Whoops. So if, sorry. This should be r sub 3 of x. So r3 of 0.5 is going to equal 0.5 to the fourth over 1 minus 0.5. So that's going to be equal to 1/8 when we compute that out, which is exactly the error, right? And so what I meant to write before then is that for any order of error, that is going to look like x to the n plus 1 over 1 minus x. So whatever order of Taylor series that we use, again, r is just equal to f minus t, our Taylor series. So those are equivalent things. We can always find the geometric error by using this computation of the sum, where we use the n plus 1th degree term. So there's obviously this relationship between the order of the series and the order of our error approximation. Something else we can note too is that f of x is equal to our Taylor plus remainder. So f of x is equal to our Taylor approximation plus the remainder. So we can rewrite this in different ways. So no, this is a really nice example where we can find the exact error. Where this will get trickier though is if we have, this summation formula expression where figuring out the sum, there's not going to be a nice closed form because it's not going to be some simple geometric calculation necessarily. So this is where the Taylor remainder theorem comes in. So let's go ahead and see if we can prove this. So we're going to do a proof of a particular degree that can then be generalized by induction. But I want to give kind of a concrete example in the proof here of how it would work in general. So we're going to suppose that f of x is equal to t of x plus e of x, where t is going to be our Taylor approximation. And we're going to use it for a particular function. So we're going to use a cubic. So our proof is going to be the cubic polynomial case. So this is going to be the third order Taylor. Oops. Third order Taylor approximation. So let's write this out. So we're going to have C0 plus C1 x plus C2 x squared plus C3 x cubed. So there's our Taylor plus our remainder term, which I'm just going to call e of x. So e of x is really the remainder of x, but we'll just call it the error term. So f of x on some particular interval I is going to be evaluated at some value, let's say c or h or z, some value that fits within that subinterval is going to be representable as the Taylor approximation plus some additional remainder term. All right, so now that we have that, we're going to just again make a note, T3 of x is the third order Taylor polynomial. Taylor approximation of f. And then e of x is going to be our error or remainder term. So error and remainder are going to essentially be kind of equivalent. So by our theorem above, we want to show that the absolute error, which is the difference in our true cubic function and our cubic approximation, is less than or equal to some number m over 4 factorial x to the fourth. So we want to show that our error is going to be less than or equal to the fourth order term, since we have a third order Taylor polynomial approximation. So we want this to be one order larger, where this m value is coming from the absolute value of the fourth derivative of f. So m is just some real number that is going to bound our fourth derivative. And note, since we're on this interval that has finite endpoints, so we're not on an infinite length interval, or sorry, an infinite interval, an interval covering all real numbers in one direction, we're going to be able to bound the fourth derivative as some finite number. So there's going to be some largest derivative value that we end up with. We're not going to have some sort of asymptotic behavior where we're approaching infinity and we have an infinite derivative somewhere on our interval. And jump into it. So we're going to go back to our constructed polynomial here. And we're going to look at values at 0. So note, we're just going to center this at 0 for good measure. So maybe so our interval is going to be somewhere on 0 and then plus or minus some value to the left and to the right. So we'll note that from our definition above, f of 0, well, all of the x terms are going to just become zeros. So f of 0 is going to equal C0 plus E0. And then we can differentiate. So kind of going through that Taylor process of differentiating and finding your coefficients at 0. So f prime of 0, so our constant cancels. Our linear term becomes the lead term. So we'll have C1, and then all the other terms go to 0. So they're all going to vanish. And then we'll have f prime of 0 is equal to C1 plus E prime of 0. And note, we're not defining the E of x function explicitly. It's just going to be some function that satisfies our criteria for approximation. So note, E of x is going to be kind of just left as a general expression. So f double prime of 0 then is going to be 2 times C2. So note that x squared term is going to bring down a 2 by the power rule. So again, we're getting kind of like 0 factorial, 1 factorial, 2 factorial, because we're just deriving these values like we would a Taylor series. So f prime of 0, f double prime, sorry, of 0 is going to be 2C2 plus E double prime of 0. Do the third derivative, so we'll get 6C3 plus E triple prime of 0. So that's our cubic term, which is going to bring down a 3 and a 2, which gives us 6, or 3 factorial. And then finally, our fourth derivative at 0, well, all of our terms cancel except for that e to the x term. So we'll have the fourth derivative of e at 0. So this is going to be really kind of useful to us. And so we're going to assume that all these values of e and the derivatives of e are close to each other, right? So we're going to let e of 0 equal e prime equal e double prime equal e triple prime. So we're going to let all those values kind of equal each other to minimize our error. They don't have to equal each other. They can be, some other values, but we'll assume that they're equal to each other just to make the values nice. So these values are going to be some really small values, obviously. And so C of 0 is going to equal f of 0. And actually, we can make these all 0 if we wanted to. Yeah, why don't we just make those all 0? So then C0 is going to be f of 0, C1 is going to be f prime of 0, C2 is going to be f double prime of 0, C3 is going to equal f double prime over 2, and then f triple prime over 6. Yeah, so note, we'll make all of these 0, although you could make them, some small, you could have some small bits of error there, but we'll assume that it's completely identical at 0. Note e of 0 should be 0 by our construction above. And so then we've got these coefficient values for our function. So we're just going to kind of use this information a little bit later, but that's going to be kind of useful to us. But for the moment, we'll just kind of put that off to the side. So let's take a look then at our fourth derivative term. Whoops, not at 0. So by our construction above, we saw that the fourth derivative of 0 is equal to the fourth derivative of e at 0. And so assuming that the fourth derivative of f is equal to the fourth derivative of e, again, that's by our construction of our cubic polynomial, but our cubic polynomial is going to become 0, is going to cancel out at that fourth derivative, leaving us with just e to the x. So that fourth derivative has to equal the fourth derivative of our function. So those two things have to be equal, and we'll suppose that we can bound them above by some value m. So m is going to be an element of the real numbers, and it's going to be a positive number since we're taking the absolute value. So we're going to take a positive real number, and now we're just going to work backwards. So we'll start with our fourth derivative of e at x, and what we want to figure out is, can we create a boundary for e? We want to bound e, but we're going to start with the fourth derivative of e. So this fourth derivative of e could be rewritten as something convenient. Oh, sorry. Not the fourth derivative. The third derivative. So if we want the third derivative, so we're going to make this assumption at the top about our fourth derivative. So then the third derivative is the fourth derivative is the integral of the fourth derivative from 0 to x plus e triple prime of 0. So let's kind of walk our way through this one. So let's note if we integrated the fourth derivative of e, we would get e triple prime of x evaluated from 0 to x. That would be e triple prime of 0. Hence this plus e triple prime that we put on the outside, that will cancel those two out. So now we're just kind of rewriting this with this integral notation to get something that is going to be able to allow us to work back to e of x. So now this is just kind of by convention here that we're drawing this. But that expression inside, if we evaluate it, is equal to that third derivative of e at x. Okay, so we know that this, if we integrate then, because we know that the fourth derivative is less than or equal to m, so this is going to be less than or equal to this is going to be less than or equal to the absolute value of the integral from 0 to x of m dx, which is equal to mx. So if we have this equaling here, and we know that e to the 4x is bounded above by m, that means that it's less than or equal to just the integral of m with respect to x. All right, so then e double prime, we can construct the same way. So this is going to be the third derivative of e to the x plus e double prime of 0, all in absolute values. So again, by the same construction, but then that is going to be less than or equal to, by our work above, the absolute value of the integral of mx dx, which is equal to m over 2x squared. Go back to e prime of x, same construction. So we'll have e double prime of x dx e prime of 0, which is going to be less than or equal to the integral of m over 2x squared dx, which is equal to m over 3 factorial x cubed. And then finally, we get back to e of x. So the bound for e of x is going to be what we end up with here. So this is going to equal the absolute value of the integral from 0 to x of e prime of x dx plus e of 0, which is less than or equal to the absolute value of the integral from 0 to x of m over 3 factorial x cubed dx, which is going to be m over 4 factorial x to the 4th. So starting from our assumption on the bounding of that fourth derivative, which is just going to be a constant value for f of x itself. So it's going to be bounded above by some number. We can now work backwards from the third derivative all the way to e of x by using this inequality process. And so what we end up with by this last the absolute value of e of x, which again is the absolute value of f of x minus this case, which is 1 plus 0 plus f prime of 0x. Oops. Let's go back here. Sorry. F of 0 plus f prime of 0 x plus f double prime of 0 x squared plus f over 2 f triple prime of 0 over 3 factorial x cubed. This is going to be less than or equal to, by our work above, m over 4 factorial. Just to the power. M is the bound for our fourth derivative of 0. That's our upper bound for that value. And that is going to give us our conclusion for the polynomial case degree 3. So note, if we started with a fourth degree polynomial, we would do the exact same work, only we'd have at the end here f5 of 0 is equal to e5, the fifth derivative of e. Right, so you just end at that different point, but we could look at this cubic polynomial and see that this is going to be constructible in every case. So again, the general idea is that e sub n of x maybe we'll use a different letter. So the actual error is this expression, the n plus 1 derivative at some value z over n plus 1 factorial times x minus c to the n plus 1. But this value is hard to find, so what we can do instead is note that this is going to be less than or equal to some value m, that again we use that m value as the upper bound for that derivative, over n plus 1 factorial, and then x minus c to the n plus 1 power. And this value here is going to be what we call the Lagrange error bound. Right, so this value is the Taylor error. But in practicality, we can never really use it because this n plus 1 derivative at z is incredibly difficult to find. But as long as we can find some boundary point for that constant, whatever that value is going to be at z, which is going to be guaranteed since it's going to be some finite number, this Lagrange error bound is going to be what we use to bound our error and essentially tell us how bad could it possibly be. At worst, it will be whatever this value is for this value of m. So note that m is, not a fixed value when we're actually working. So m is, arbitrarily close to this derivative. Right, so we want to get as close as possible to that n plus 1 derivative. So, usually m is going to be something that we can guarantee is above, but it's not too far above, right? So m is not going to be 10,000, right? If we know that this derivative is bigger than 6, then we're probably going to make this slightly bigger than 6, maybe 7, maybe 6.5. It kind of depends on our confidence in what we know about the values. So again, you don't need to know the proof here, but this is kind of one way of deriving it that we could then extend by induction. And these values kind of appear in the end of our work, but we're not going to spend too much time going through them. But they generalize as well. And so what we end up with is that this remainder term, whatever it is, can be bounded by the Lagrange error bound. That's really where we're going to care most about it. So again, the main idea is really going to be getting us here to that expression and calculating it. And that it's going to be the next. So note, this is the next term. The next Taylor polynomial term in the series is kind of how you can think of it. Wherever that next term shows up. All right, so I hope that this was somewhat helpful if you're watching this video. If not, come by my office hours and we can discuss in more detail. And so until I